Hello everyone, how are you? Great. Oh, you can't see me. Here we go. Oh no, let me turn on my video. Just a second. Hello. Hopefully you can see me now. Now. Okay, nice to see everyone. Okay, right. So I know that there are some questions about the exam. So let me quickly say there will be an exam on Friday. People might be curious what's on the exam. Actually, what's on the exam is going to go from the recursions onward. So after the last exam, we had then a class which was about Fibonacci's. So anything from that class starting on all the way up until what we'll cover on Wednesday. And if you're practicing the old exams to go and get an idea of what this is like, you will notice there are some questions on the old exams which have something to do with these like parentheses. Don't worry, we're about to learn that today and on Wednesday. So that's what we're going to do. Okay, and the exam is Friday. It will be the same kind of thing as before. The advice is, I will try to make it less, not quite as hard. I'll do my best. And then the general advice is the questions are supposed to be, in some sense, like easier to harder as you go on. Okay, are there any general questions about the exam first, if I can answer them now? I'm going to say one thing, which is that you're not going to need to know how to take a matrix, all the matrix stuff. It's going to be useful to know, I guess, that the matrix multiplication thing was useful, but we're not going to go in deep into these like Vandermonde type determinants or whatever. So it's going to be designed in a way so that even if you haven't taken a matrix class, just based on what you've learned about matrices from high school, it should still make sense. But the notion of matrix multiplication, I think that would be something that would be fair game. So we will do something on that order. Okay, cool. So I want to just go on and give you guys I want to give everyone the big theorem that you can use, and you can use it without proving it again, because the way that this class works is if we have covered something, then you can just go ahead and use that. 1 second, I just realized that I gave a talk on the weekend which had different background. Let's do this. Here we go. Okay, good. And let's go on from where we were last time. So I have here an extended slides, because that's just this is just like the last few days that we've had. And we managed to find out that if you, for example, had a recursion that looked like this, where the little a(n) is equal to some capital A(n) minus 1, and then so on and so on and so on, it turns out that there's a particular way to do this with generating functions, and what you end up getting is this kind of a denominator. Just realized I should turn on a light. 1 second. Okay, that light's on. So you should turn on this. So you should use this denominator, and from the denominator, what you can get is that it becomes a question of finding the roots of a particular polynomial. This is the characteristic polynomial, and so now once you found these roots, it turns out that if all of the roots were different, then the answer becomes that the general term is going to be this combination of the powers of those roots. And what to do if those roots are the same? Well, then we started to find out that there were some other interesting things you could do. And the punchline that we got to from everything was that if you wanted to find out, let's just go here. We took some derivatives also. Whoops, let me go back. Where was that? Ah, yeah, that was here. So what we found out is that if you actually have so there's some garage door underneath me which is making noise. But what we found out is that the coefficient of z to the power n, which is going to be your a sub n, is going to be some polynomial whose degree is up to the number of repetitions of this root. Actually, degree, the number of terms, like the constant, the n squared, that's up to the repetition of the root many times, and then times the particular root to the nth power. Now I'm going to say all that we did before justifies what I'm going to write down next. So what we now know is that here's how you solve. To solve a general linear recurrence, all you have to do is you just go and say, well, I have some, you write the characteristic polynomial, which is something like lambda to the n minus, then you have a bunch of things that you write. It was like this capital A, lambda to the n minus 1, minus capital B, lambda to the n minus 2, minus dot dot dot, minus, I don't know how long it goes, z or something. I guess n is equal to 26 maybe, something like that. But so I have this thing. And then you write this characteristic polynomial down. Remember, this means that what you had is that this was from a particular recurrence, which was little a sub n is equal to capital A, little a n minus 1, plus capital B, little a n minus 2, plus dot, dot, dot. That was the kind of recurrence that we had. You write this down. Then what do? Then you find the roots, which now you can tell that I'm not going to put this kind of a pure problem, like with a big number of terms on an exam, because nobody remembers the cubic formula. You find the roots. And the roots, what we'll do to separate these out is we'll say that the roots, they come as some distinct things. They are lambda 1 with multiplicity let's call it m1, and then you have a lambda 2 with multiplicity m2 all the way down to lambda, I don't know how many roots there are, maybe r for the number of roots, with multiplicity mr. And the important thing here is that these are distinct. Right? So you go and find the distinct roots. And now, can someone just like remind us, because our brain is a little bit slow from having had a extra break on Friday. In light of everything we've done, what does that mean? Then for any n, I know that a sub n is equal to something. What's the form of what I should have here? Based on what we've done, based on what you've thought about. You know, you would generating function this thing, you would get like this partial fractions thing. Braden.
It's the sum for each lambda of lambda sub r, or lambda sub r, n times some polynomial that has degree 1 less.
Yeah. So what we'll say is that it's multiplicity m1, right? So I'm a visual person, so the way I'm going to write that is there's some coefficients now. So they're blobs, okay? So it's like a blob. I'll write a parentheses here. Blob plus blob n plus blob n squared plus dot, dot, dot. And what you have here is you have m1 of these, m1 terms, times lambda 1 to the n, plus, and you do the same thing for all of the other roots. So the next one is like blob plus, don't know how many of the blob terms there are here. Well, let me write it still the same way. Blob n plus dot, dot, dot times lambda 2 to the power n. And here you have m2 terms, and so on, until lambda r stuff. Is that clear to people? First of all, does the theorem make sense to people? Does the statement of the theorem make sense to people? The purpose of the theorem is to say, I find all my roots. And after I find all of my roots with different multiplicities, then I just have to fill in these blobs. And the number of blobs that I have has to do with, so for every lambda, the number of blobs I have has to do with the multiplicity of that particular root. And if you want to remember why, the basic idea was because you were generating functions this thing. When you're generating functions this thing, you would go and get some partial fraction decomposition. The partial fraction decomposition will have powers of like 1 minus z times lambda 1, that to some power, that particular power being all the way up until m1 power. And what we saw last time is that if I wanted to know what's the general form of a coefficient of an expression like this, I'm going to flip back, of the expression like, 1 over 1 minus z to the power r, the general form of that actually just has some polynomial in r whose degree goes up to the multiplicity minus 1. And then we just combine the blobs, because what we have here is, if you wanted to combine all of these different partial fraction pieces, you'd be adding together a bunch of different polynomials in n, whose degrees are all less than or equal to the multiplicity minus 1. And then the blobs would just become other blobs. So then you have this piece. And this ends up being the general form. And if you want to know the actual blobs, you can just solve a system of equations. You plug in the first Well, it's not n terms, but you plug in as many terms as you need as there are blobs. Plug in as many values for n as there are blobs, and you get the values of the blobs. And that gives you a formula for all n. So that's the grand finale of this homogeneous linear recurrences. Are there any questions about this? You can use this without proof, although it's very useful to understand the proof, in the sense that if we have something that digs a little bit deeper into why one of these things is true, then it would be nice to understand a bit of the proof. But if you ever run into a recurrence like this, you'll be able to deal with it. Question, Thomas.
I just wanted to ask, like, just to make it more specific, so, like, if we had, like, a two-term linear recurrence with a repeated root, then you would get that an is blob plus blob n times lambda squared, where lambda is.
Times lambda to the n.
Right.
Close. Yeah. So the n here is the same as the n in the an. Yep, but exactly. If you have a very precise question, which is like, suppose that there's one repeated root with multiplicity 2, and that's it. Then in that case, you've got no more of this nonsense. It's just blob plus blob n, close parentheses, times the root to the power n. Find the blobs. Yes. It's amazing. Actually, it's amazing. But the first time I ever learned this, I was like, oh my gosh, you can actually solve all of these recurrences where all you have to do is find the roots of the polynomial. That's amazing. It's actually solvable. And we, in fact, have done in this class enough of the understanding of why that's the case, because it just comes into the question of like how you deal with these partial fractions. Over here, we saw all of these things. Any other questions on this core piece? If not, let's go on. So I want to make sure we have time to cover the next major topic. The next major topic is about how many ways can you arrange parentheses to be legit? So how many valid arrangements of n pairs of parentheses? Okay, well, what does that mean? So let's give some examples of valid. Open, open, close, close, open, close. But bad would be like open, close, close, open, open, close. Yeah, that works. What was so bad about this? What's bad about the bad? Yes. Nick.
The second close doesn't have an open before it.
Yes. Like, what's that? That's funny. You've got this thing here where we have closed before opening. Your program will not compile. Okay. So that's why it's bad. And so that's pretty easy to understand the question. It's just how many ways can you arrange them? Well, let's try to work this out. If I want to know the answer to this, it helps to get some small cases to try to find out the answer. So what is the n equals 1 case? That's easy. I'll do that one. There's only one. There's only one way. It's just open, close, and so it's just 1. How about n equals 2? I don't want to use the yellow. Let's just use blue. N equals 2. Can someone help me? What are the legit sequences of parentheses for 2 pairs of parentheses? Has to be legal, valid. Ising. That seems about right. So, okay, let's call that 2. The next one, how about n equals 3? If you just want to say a few of them, that's fine. You don't have to have the answer. Yes, we got someone. So, Charlie.
Well, you have open, 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 close, close, close. And then for the other ones, you can just add n1 to one of the 2's.
Oh, this is very interesting. You're going to build it from the previous ones, okay? So what did you say? So you got the triple open, triple close, and what else?
All the other ones is going to be 1 from n equals 2 and 1 from n equals 1.
Oh, so you're like, the way that I make it is I go and combine an n equals 2 and an n equals 1. So let's try that, right? So if I combine an n equals 2, I'll use colors since you suggested that. So I can do open, oops. I can do open, close, open, close. That's an n equals 2 and an n equals 1. N equals 1, there's not much choice. And I have open, open, close, close, open, close. Is that it? Or do we have more?
You could do the like other direction where you do the n equals 1 first,
Like that.
but you're gonna overcount by 1.
Ooh. Okay. So is that it?
I think so.
Okay. Does everyone agree? Or is there something else here? I actually think there's one more. Ben.
Yeah, where's open, open, close, open, close, close.
That. Oh no, let me do it a different way, okay? That's like,
Is that wrong?
I'm doing this. Do you see what I've just done here? So what we just did is we kind of sandwiched one and the others. That's no fun. So this is actually like not fun. The answer here is 5. What sequence goes 1, 2, 5? Come on, at least it could have been Fibonacci 1, 1, 2, 3, 5, but it goes 1, 2, 5. I just happen to know that with this particular sequence, it does go 1, 2, 5. Oh no. Now it looks complicated. By the way, the idea was quite good of like, you open and you close. But can we try to find some other way of doing this? Oh, what is this? Braden. But skip every other number. Yeah. Okay, that's it. Clearly, it's Fibonacci numbers skipping every other number. That might be the case. Well, it turns out that this sequence is actually famous. So I'm going to slip at some point when I say it. So let's just say it right now. These are called the Catalan numbers. And the Catalan numbers are extremely famous because it turns out that there's a lot of things where the number of them turns out to be this, the number of ways to arrange parentheses, where you have these n pairs and they have to be legit. And so Catalan numbers, if you look it up, you'll see all these different things that they can count. They count things like triangulations of polygons and whatnot. But now it's important to go and try to answer, how many are there? And as you can see, we're already trying to think inductively. How do you build it from the previous one, right? And here we were trying to build from the previous 2. Well, if I look at this, can I find any other way to try to figure out a recurrence for the Catalan numbers? Well, let's go and hunt for recurrence. First of all, let's call the Catalan numbers Cn. Okay? So let Cn be the number of valid pairs. That's not how you spell pairs. Pairs of, oh no. Number of valid ways to make n pairs of parentheses. Number of valid ways to make n pairs of parentheses. Okay? Now that's the Catalan numbers. How could I try to count those? Well, I had some colors before. Advait, what is this? You have something you want to say.
I have an idea on how to count them. I wasn't really thinking about colors, so this might be like kind of sideways compared to where you found out.
Oh, no, don't need any colors. I was just going to use colors to make the idea clearer. But tell me what you were thinking.
But so like if you go back to like those parentheses, yeah, you see like the second, you see like the third one in n equals 3. That's like a thing of 2 and a thing of 1. So what if you split 3 up into 2 and 1 and made like the number of ways to make 2 times the number of ways to make 1, and then sum up over everything that adds up to 3.
So you're like, the way I make 3. Okay, let's stare at this because let's understand how this is a neat question. Okay, so one way I could try to approach this is I could say, oh, look at that. It's a 2 and a 1 because that was the idea that Charlie suggested, right? So if I have a 2 and a 1, how do you make 3? Well, 3 is made in a few ways. 3 is equal to, well, let's do it this way. So I'll use some other color here. 3 is equal to 2 plus 1. That's one way. And in fact, I'm going to say that this particular one here, this is a 2 plus 1. How else can you make 3? Another way to make 3 is 1 plus 2. But I'm going to say this is where it gets kind of tricky. Because how do I characterize this one? I think that's why Charlie might have said there's like two ways to account for things. Because you see, the one that I just pointed in this pinkish thing, this is both a 2 plus 1 and a 1 plus 2. And that's not fun. If you have two different ways of counting the same thing, then it gets annoying. Oh, Chris, you have a hand. What did you want to say?
So, for every of the previous, you can either place the parentheses around the whole thing or them after. So then you get some kind of tripling. But for the case where it's open close, open close, open close, adding to the beginning and the end is just the same. So maybe it's something like 3a and minus 1.
Ah, so what you're thinking of, like, somehow you're like, you put things around the end. Are you sort of thinking of like how you make the end, the open and close?
Yeah. So you like function compose it.
Okay, so now we're starting to think of like, where are the parentheses? How are you function composing them, right? So let me take the n equals 3. Let me rewrite those, okay? So I have n equals 3. So this is C3. Whoa, wrong pen. C3. And here I'm just going to draw them in the same order we had with no special colors. Open, 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 close, close, close. We also had open, close, open, close, open, close. We also had open, open, close, close, open, close. And then we had open, close, open, open, close, close. And then we had open and close on the outside and open, close on the inside. Okay. Great. So I've got all of these. Now, when you look at all of these, we can start to think of how you're composing, how you're function composing these. And we do want to build this up from smaller things. So here's a suggestion. I'm going to give a hint. I want to think about the first one. What's the partner of the first one? Let's start to do this together. In this first line, what's the partner of the first one? Nick.
The very last close.
Okay. Next one. This one. What's the partner of this one? Well, I guess people know this. I'm just going to kind of highlight them, right? It's the one that came right after it. And then here is one where I have the first one. Ah, Isain, why don't you give me this one? What's the partner of this third one? Yep, all the way over there. And then, I'll do the next one. This is easy. And I'll just do this because I think people understand. I've just marked the opens and the closes for the first guy. Why is this relevant? Can anyone see why this is useful? I can use this to break things apart. My goal is to be able to say C3 breaks into a sum of some things. So I want C3 is equal to a sum of a few things. How can I split this apart? Sydney?
I'm not exactly sure, but would you say that like every time you take something from the previous one, you can put the left parentheses like anywhere, and then you make sure the other one goes to like the right of it?
Aha! So you're like, take something from the previous one. The left thing that you wrap around it can go anywhere, and the right one goes somewhere after it. Okay, good. I'm glad we're thinking about this. I want to be able to split into cases. I want to say like any legit parentheses thing breaks into, it's going to be this or this or this or this or this. I'm giving a hint. It's not actually just the sum of three things. We just did these linear recurrences. This is not going to be a linear recurrence. It's going to turn out that the Cn has to do with a lot of previous Cs. And we've got another person, Nancy. Oh, could you speak up a little bit? I want to hear what you said.
For each of them, there's like a unique way of breaking it up so that if you look at like a set of parentheses, and that can't be broken down any further, and then you can take the products of stuff.
Okay. So I heard the key words of like, I want to take the first parentheses, I want to take the product of stuff as I break down. What I can do is I can break into a few cases, which is called, do you close the first one right away? Do you close it after one pair? Or do you close it after two pairs? Do you see that? I have three categories. The categories are, you close the first parentheses. How do you spell parentheses? Parenthesis, maybe. Close the first parenthesis after the number of pairs is equal to 0 or 1 or 2. Is that okay? So it's like I will, and this is, for example, a 0. The number of pairs that I got, I should be clear. The number of other pairs. Do you know what I mean? Like the number of enclosed pairs. Let's do that. Enclosed. The number of enclosed pairs. That's how I'm emphasizing that this second row, that's the 0 enclosed pairs. Yeah? And then this first row, that's 2 enclosed pairs. By the way, the 0, 1, 2 is only for C3. We're going to have to do this in general for all of the different Cs. So how can I turn this? I want to do multiplying. Advait, help me with this. If you close it after 0, what is it?
So it's like C0 times C2.
Ah, you just invented C0. Well, we need to know what is C0 because, I mean, like the number of ways to arrange 0 pairs of parentheses. What's that? How many ways are there to arrange 0 pairs of parentheses? One way. Okay? There's one way. That's important because it's always important, like what's 0 factorial? What's 0 choose 0? Here it's convenient to say I want C0 to be equal to 1 because if I look at my second row here, that's like one way to enclose no parentheses. And then I've got a C2 because there's 2 pairs of parentheses left which are following it. And what we just did here is we said C0 equals 1.
And then you get, for the next one, you get C1 times C1, and then C2 times C0.
Oh,
You have this ascending, descending looking thing, which is good.
so this is cool. This is going to generalize, right? We did it for 3, so it must be true for all of them. 3 is not quite 7, but it's close enough. And the important thing is what we've just found out is there's this beautiful pattern. And I want to pause here because this is a very important point. The important point is like, look, if I have C3, I have actually legitimately split up all of my possibilities just based on the partner of the opening parenthesis. And every possible way of doing this, the opening parenthesis must have a closing parenthesis. And it just has to be somewhere. And it's just like, is it after 0, after 1, after 2 pairs? And so what you see here is it's going to be true in general. So what I find out is, in general, Cn is equal to, well, let's call it Cn. Yeah, why not? Cn is equal to C0, Cn minus 1, plus C1, Cn minus 2, plus, you just kind of like swap between them. It's almost like a binomial theorem-ish kind of thing. You know what I mean? Like the sum of the indices, they trade off against each other, all the way until the last one, which is Cn minus 1, C0. Okay, so that's the recurrence for the Catalan numbers. And now the question becomes, how can we find out a formula for the Catalan numbers? Well, what tools do we have? Can we use linear algebra? Yeah, we're going to have to use some generating functions for this because linear algebra is going to be bad. If you try to imagine trying to have a vector which is just like the C's, okay? If your vector was just C0, well, what would it be anyway? It's not like it's a fixed length. You know what I mean? When we did the linear algebra, we were like, my recurrence always has 3 terms. So I will go and take 3 things in my vector, always 3. But here it gets longer and longer. If I want to know the recurrence for C100, there's like 100 terms or something like that. Yeah, C3 has 3 terms. C100 has 100 terms. So I want to find a different technique. Let's try generating functions. So now I'm going to rewrite this recurrence relation on the next screen. Okay, so what I know is Cn is equal to C0 Cn minus 1 plus C1 Cn minus 2 plus dot 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 plus Cn minus 1 C0. That's my recurrence. And by the way, all I have for my initial condition is just C0 is equal to 1. The beautiful thing is just from C0 equals to 1, you already get the whole formula. Because if we wanted to know what would happen next, right, the next term would have been C1 is equal to what? What would I have done for C1 if I used this recurrence? Anyone want to tell me? I just want to get everyone comfortable with this, and then we'll do some generating functions on it. Ah, yes, Nick.
C0 times C0.
Okay, C0 times 0, C0. And that's equal to 1 times 1, which is 1, which is good. We had that last time. C1 was 1. The number of ways to arrange one pair of parentheses is 1. And whenever I do something like this, I always want to sanity check. Does it work for C2? I'll do this one. C2 is going to be C0, C1 plus C1, C0, which is 1 plus 1, which is 2. And the moment of truth is the the C3, do I get 5? C3 is supposed to be C0, C2 plus C1, C1 plus C2, C0, which is equal to, well, I will take the 2 times 1, that's a 2, plus a 1 times 1, that gives you 3, plus another 2, that's 5. At this point, we should believe it. And of course, we should believe it because we did it. We derived this thing. So now the question becomes, what's the generating function for this? So let's let f of z be equal to, well, it's going to be c0, z to the 0, plus c1, z to the 1, plus c2, z squared, plus ... I'll write the third one. c3, z cubed, plus ... But oh no, now I can't do what I did before. What I did before is I just replaced each thing by like some, well, I guess I could. I can replace each thing by like some combination of the previous ones, right? But the combinations now aren't just like summing 2 things or aren't just summing 3 things. And so the key question becomes, have you ever seen in algebra, ever done anything before where you might somehow do this? Is there anything I can do to the f? I want to do something to the f to go and, make this thing appear. I'm like, I want something I can do to f. And let's see. Any thoughts? I want to give other people a chance if I see. So Venkatesh, what do you have a thought of?
You can square it.
What happens if you square it? Well, f of z, whole thing squared. Let me do parentheses, okay? Just so that we know what I mean, or brackets. I want to square it. What is that? Well, I'm going to have to do some big multiplication. So I'm going to write this all out a little bit. C0, z to the 0, plus C1, z to the 1, plus C2, z squared, plus ... times the same thing again. C0, z to the 0, plus C1, z to the 1, plus C2, z squared, plus ... Okay, how does multiplying work? Well, I need to know I'm multiplying 2 infinite polynomials. That's called FOIL. It just never ends. Anyway, so if you want to do this thing, you're going to take one thing from each bracket, right? And if I want one thing from each bracket, here's how we should start thinking about it. How do you get a z to the 0? If I'm going to grab one thing from each bracket, how can I get a power of z that is just plain z to the 0? I want to get as much involvement as I can in this because this is like one of the core ideas in how we're proving this generating function thing. Good. Dhruva. Yes. The important thing is how could you possibly get z to the 0? Well, you're going to take more z's and more z's. You just get more z's. So you better take just the z0 thing and just the z0 thing, and 0 plus 0 is the power of z. It's still 0. So what you end up getting is just C0, C0. Those are both zeros. I'll do a plus sign. Actually, I'm going to write the z to the 1 outside. I want a parentheses. What's the coefficient on z to the 1 now? How does this work? Can someone else help me out? I want to get as many people involved in this as we can. How do you get a z to the 1 term where you grab something from each? Brayden.
So you can either take a C0 and a C1, or you can take C1 and C0.
Right? These are the only ways, the blue and the pink are the only ways that you could get a power of z, which is z to the 1. It's a 0 plus 1 for the power of the z and the power of the z, or a 1 plus 0. This looks familiar. Okay, and our instinct is this has to work, right? Plus z squared. Oh, yes, of course. That's actually why these c's have the indices, which always add up to the same thing. Because I'm just kind of, the way you multiply polynomials is you kind of move in opposite directions on both of them, right? I'll do this one. So this one is like, how do I do this? Well, I know I want to get a z squared. So to get a z squared, I either take z to the 0 from the first and the z squared from the second, or I take a z to the 1 from the first and a z to the 1 from the second, or a z squared from the first and a z to the 0 from the second. And that's exactly what I wanted. That's C0, C2 plus C1, C1 plus C2, C0. It's annoying that the C's look like parentheses. Okay, so now that I have all of this, I'll write a plus dot dot dot. Okay, well, in light of all of that, what's the punchline? What's the conclusion? This is pretty exciting. Advait, what do I now know?
Looks a heck of a lot like f of x, just divided by z and without the first.
Okay, so the important thing is like, it looks a lot like f of z, except that the first thing would give me a c1, right? I would have gotten c1 z0. Oh, let's do this. I want to make it so it's as easy for you guys to read as possible. I'll write an equal sign over here, and I'll write c1 z to the 0 plus c2 z to the 1 plus c3 z squared plus dot dot dot. And now I'll write the equal sign equals, you said it was like f of z over z,
Without the first term.
but without the first term. So let's expand this and write minus c0. Is that what you want?
Yeah.
Because if you think about what is f of z starts from c0 z to the 0, okay? But then it goes c1 z to the 1, and you go on this, like all this blue stuff. But I need to drop a power of z because all of the powers of z in the blue stuff are 1 down. But I know what I know what c0 is. C0 is 1. So now I know that this is equal to f of z minus 1 over z. So our goal is to go and figure out what is the Taylor series for f. And actually, we can solve for f now. We can find the generating function in the sense that f is not going to have a plus dot 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 anymore. I have an algebraic expression. I have that f of z whole thing squared is equal to f of z minus 1 over z. Let me rewrite that final expression on the next screen. Just giving people a moment to pause and take this in. All we did, by the way, is just called, it looks like the pattern for a square. Let's square for fun. Oh my gosh, there is f again. Okay, that was the key thought. And then now it's like, how do I solve for f? Well, let's write that down on the next screen. I know that f of z whole thing squared is equal to f of z, I'll write a bracket around it, minus 1 all over z. Any thoughts? I need to know f of z. I need to get like f of z equals something so that I can go and have my Taylor series fun. What would that be? How can I solve for f of z here? This is like a thing that is, there's a one twist in here, which is a strange thing that you would ever do with functions in an equation. But I emphasized with like a bracket. It's like a square bracket. Chris? The quadratic formula on f of z. Yes, why not? So first of all, let's turn it into a quadratic equation. Multiply both sides by z. I have z times, I'm going to use colors now, okay? This is the square bracket f of z. Oh, I have a better idea. Oh yeah, that's okay. Square bracket f of z. My square bracket is in blue, but my exponent is in white. Because I'm emphasizing that my unknown is square bracket f of z. And then I'm going to minus the square bracket f of z. And then I plus 1 equals 0. I think I didn't make a mistake. So what we have here is we're just simply saying multiply the z up, okay, and then shove everything back to the left side, and I've got this. And I have a quadratic equation in f of z. So that means it satisfies the quadratic formula. Whenever you have blah 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 times unknown squared plus blah 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 times unknown plus blah 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 equals 0 by the quadratic formula, which you can prove by completing the square if you want, or other methods, you can find out that, so f of z is equal to negative b, right? Negative b is the negative of the coefficient of the f of z, of the blue thing, plus or minus the square root of b squared, that's 1, minus 4 times a times c, that's 4z, all over 2a, which is 2z. Are people okay with this? Something fishy. What's fishy, Advait?
Plus or minus.
What's plus or minus? Yeah, hang on a second. We're supposed to have just one generating function. Why is there a plus or minus? That's no good, because it's like, it's a thing, right? There's not plus or minus. So should it be plus or should it be minus? And is there any way that we could figure this out? And this is why I'm saying, like, in this generating functions thing, some of the things we do are not necessarily the most rigorous, but they seem to make sense, which is enough for this particular unit. I need to figure out whether to use plus or to use minus. Well, we need to figure out whether it should be plus or it should be minus. It should be one particular one of them. Well, what happens when z equals 0? Does anyone know what happens? And this is the one fishy thing about the generating functions I'm about to do. What is f of z at 0? What was f z anyway? Remember f of z? That was the Catalan thing. It was c0 plus c1z plus c2z squared, and so on. What is f of 0 supposed to be? This is actually not really, it's not a trick question. Nick?
C0.
It should be c0, right? Like I can substitute in 0. That's like, that particular power series. Actually, there's an interesting thing here. If you're curious, how is that even rigorous? The answer is because it has to do with the fact that there's a radius of convergence on a series. So for example, if I plugged in z equals 50 million, this thing is just going to be like infinity. But there's actually a small radius of convergence around 0. Because actually it turns out that the Catalan number Cn is always less than like 2 to the power 2n. I'm just making this as a general comment. It's useful. It's like the number of ways to arrange n pairs of parentheses is always less than 2 to the 2n. Does anyone know why? If I'm going to put down n pairs of parentheses, so I'm going to make that a sequence of 4n things, and it's going to be n pairs of parentheses, and they're like legit. Why are there at most 2 to the power 2n of them? Dhruva?
Because 2n is the total number of ways to solve the parentheses.
Yes, it's because if I just have 2n things, and I decide to be like open or closed for each one, and I don't even care if it's legit or not, the number of them is 2 to the 2n. So I'm just making this comment. I'm not writing it down because it's just a general comment of like, why is it true that you could imagine that there's a radius of convergence? It's because the size of the Cn is always less than like 4 to the n. And from calculus class, there's like the nth root. Is that an nth root test? Is that right? For like convergence of radius of convergence of power series. It's been like 20 years since I took that class. But it's like there's some nth root test. And the nth root test would tell you that your radius of convergence, you have at least 1/4. Anyway, I'm just explaining this. This is not important for the class, but just so you know, we're not like totally cheating. Okay? So you can actually plug in 0, and it should make sense. But it's just plain 1. Okay, why did I do that? I claim you can use that to figure something out here. Chris, you had raised your hand. Did you want to answer this, or were you answering that?
Yeah, so when it's 0, I think you get 1 plus or minus 1 over 0. And, well, if you get, so your two options, either 2 over 0 or 0 over 0. And I think we prefer 0 over 0 because it lets us define, like, oh, it just doesn't know what C0 is supposed to be, so it's letting us choose.
Okay, well said. So the point is 2 over 0 is very bad. 2 over 0 is very different from 1. What I'm saying is that 2 over 0 and 1 are totally different planets. 2 over 0 would be suggesting that something is diverging. But 0 over 0 is a sign of something called a removable singularity. It's like if I wrote down some expression like z over z. Actually, z over z is legit, except when z equals 0. The rest of the time it's 1. So that's actually what I meant when I said this radius of convergence. If you wanted to know why this is rigorous, the way you'd actually do it is you'd go and argue and say, well, you know, although I can't really put in 0, I can put in a number onto the Taylor series for f, the generating function, which is so close to 0 that this is really, really close to 1. It's definitely possible because there's this radius of convergence, and so it's actually close to 1 when you're really, really close to 0. Therefore, if I put a number here, which is really, really, really close to 0 for z, then I'm going to get a number on top, which is really, really close to either 0 or really, really close to 2. And I don't want something really close to 2 dividing by something really close to 0. So that's the easiest way to explain why it better be a minus. Ooh. So there's a question here about like, what happens? Does it turn out that some of the terms are real, but the thing is also complex? Well, actually, the real problem is it just does not converge, right? Like if I went and put in a number like 50 for z, it just goes to infinity. And infinity is not a number. So it's not even that it went to a complex. It just went to not a number. Okay? But this is justifying why it should be minus.
I think Sebastian's means,
Oh, he means something else.
inside the square root.
Oh, okay. So inside the square root. Oh, that's also interesting. Huh. Okay, I didn't think about that one that carefully. It's like, well, is the answer then complex? I think the best way to put it is actually once you get like beyond the 1/4, it might start falling apart in the radius of convergence business, and we might be getting like weird stuff. We might be getting like infinite stuff. So that's why I'm saying like with this thing, we don't actually go and discuss too much of the convergence things. I just mentioned that in case people were curious about these things. But I'll write, and 2 over 0 is very bad. Okay, so what we now know is we now know that f of z is equal to 1 minus the square root of 1 minus 4z all over 2z. Okay, so now if I want a formula for the for this Catalan number, all I have to do is take the Taylor series of this. Fun? No, this is terrible. We don't want to do that. Instead, what we'll do is we'll use the fact that we actually had touched on something quite similar in the previous class, where this term, 1 minus 4z to the power 1/2, is actually very interesting. It turns out that there's a nice way to Taylor seriesize just this part, 1 minus 4z to the power 1/2. And we'll do that to finish up today's class, and then we'll continue again tomorrow, and on Wednesday, and we'll get the full theorem. So what I want to do is I'm a little bit curious. What happens if I have something like 1 plus z to the power r? That's what we want to know. Taylor series. Because by the way, I wrote 1 plus z, but what we really will want to do is we'll want to do 1 minus 4z to the power 1/2, right? So we will actually use, somehow like minus 4z instead of z, and we'll use 1/2 instead of r. Okay, but this is a very general thing. I want to get this general thing. Oh, Venkatesh, you were going to say something. Maybe? Never mind. Okay. Yes, and Advait says this is the generalized binomial theorem. Well, let's try. Okay, I want the Taylor series. We're going to get a new name. This is called g of z. G of z is equal to this. How do you get the Taylor series? Well, we just start to, take derivatives. So I have g of z. Well, we just got that right there. I'm just going to rewrite it. Well, I won't write the of z. I'll write g. Oh, I do want to write the of z. Do I? No, I don't need to. I'll just write g. G is equal to 1 plus z to the power r. Actually, this is just like what we did on Wednesday. I want to take evaluations at z equals 0. That's not so bad. At z equals 0, what is 1 plus z to the power r? It's just 1. 1. I can do that. How about g prime? What's going to happen here? Can someone help me out? What's g prime? This is just Taylor series. I want to take a whole bunch of powers, a whole bunch of derivatives of this, and I want to keep plugging in z equals 0. Braden.
So we can get rid of it to get r 1 plus c r minus 1.
Okay.
And then if you evaluate that at 0, then
So that's nice. Actually, what you're seeing here is evaluating at 0 is not bad because I have a power of 1. And if I keep going, g double prime, that's equal to, I'll do this. This is r times r minus 1 times 1 plus z to the power r minus 2. And if you evaluate this at z equals 0, that's r times r minus 1. Okay. But by the way, if you do these Taylor series, we already see what's going to happen. It'll be 1, r times r minus 1, and so on. Let's just write the third one, okay? The third one, I'm just going to write g triple prime, a big long arrow, and then what it actually is, which is r minus 1, r minus 2. Now, how do you go from this to the Taylor series coefficients? What should I be doing to each of these things if I want to get the Taylor series coefficients? Advait. Divide by the number of primes factorial, where you mean like the number of derivatives factorial, which is 1 over 0 factorial, 1 over 1 factorial, and that becomes r minus 1 over 2 factorial, and r minus 1, r minus 2 over 3 factorial. Why is this Exciting. What have I just written down? Dhruva.
That is R choose 0, R choose 1, R choose 2, R choose 3.
R choose 0, R choose 1, R choose 2, and R choose 3, where we've been very liberal with how we're defining choose, okay? Because remember, R is 1/2. We have just defined a reasonable way to say, what is 1/2 choose 3? You just stick it in there, okay? So it's like, you're not really choosing things, because 1/2 choose 3. How can you possibly choose 3 things from half a thing? But this is the generalized binomial coefficient. That's what these are called. So these things here are called generalized binomial coefficients, which are of the form real number choose, I guess, non-negative integer, which is like, oh no, how am I going to write that? There's not a good symbol for non-negative integers. I'll just write z plus union the 0. I'm just trying to emphasize that I can throw any real number I want in the top now, and that's just how I'll define the choose. And that just gave you, Subhashish says kind of. What is the kind of? Yeah. So the deal is like, if I use this, it's okay. And that's why n should have 0. Okay, so some people think that natural numbers should have 0 in them. Yeah, it would have been convenient. But, oh, you know what? Some people actually have a notation for this. Let me just use that, okay? Some people actually use z bigger equals 0. Have you seen that before? This is a pretty good notation. It's obviously shorter. But now what I've just found out is I've gotten the Taylor series. So I've just found out that 1 plus z to the power r Taylor series is, okay, Taylor series time, I put all the coefficients in front. R choose 0 plus R choose 1 z to the 1 plus R choose 2 z squared plus R choose 3 z cubed plus forever. Now, why should this make you very happy? There's something about this that makes you very happy. It's like, okay, kind of cool. I've got all these like R choose stuffs. Have you ever seen anything before which is of the form R choose 0 plus R choose 1 times z to the 1 plus whatever? Actually, we do care about 1 plus z to the power 50. The regular binomial theorem. You know what happens? If r is an integer, I know how to do this. If r is an integer, I just like write these things out, but then I stop. So why does this stop? What's the deal here? What does this have to do with regular binomial coefficient? I'll write note. If r is a legitimate integer, okay, non-negative integer bigger or equals 0, then what happens? I have an infinite sum, don't I? A lot of zeros. Yes. Because eventually you get 0, right? If r is an integer, then eventually the coefficients are like, I'll just write something. 7, choose 99, which is just 0. Okay? I was just doing like r equals 7. That was what I was doing. It's like eventually you just get like stuff, choose bigger stuff is 0. So actually it's just the old-fashioned binomial theorem. What I'm emphasizing is if you're taking 1 plus z to a legit non-negative integer power, you just got back the old binomial theorem. And so what this is this is a generalized binomial theorem. One thing to be careful about is about radius of convergence. This is a little bit bogus if you plug in a z which is too big. Let's not worry about that. We're doing these like generating functions things. But there's a name for this if you're curious. Some people call this Newton's generalized binomial theorem. And so that is actually the heart of what we're about to use when we come back on Wednesday. We're going to use this piece, which lets me go and take 1 plus something raised to a weird power like half. We'll use that to just in one punch knock out the nth coefficient for this Taylor series for the Catalan numbers. And we'll continue next time. Next time we'll finish up Catalan numbers and we'll be all set with everything we need for the exam on Friday. Great.
Thank you.
Yep.